Section 1.4 talks about curve sketching. So this is a quick reminder, a few types of graphs, 3 to be specific. One, the parabola, so y equal x squared. When we say sketch, and that's the majority of the time what we want in this class, a rough graph will be. If I see a +2, so that's going to shift the graph 2 units up. That would be moved 1, 2, and you would give me an identical graph to that. If I see a negative in front of x, that would indicate that the parabola is upside down, and the 3 will shift that up 1, 2, 3 units, and the graph would look something like this. Now, instead of have y equal x squared, we could have x equal y squared. If I isolate x by itself, x equal y cubed over 3 is a parabola at the origin. When you say y equal x squared, the graph is wrapped around the y-axis. But if you say x equal y squared, the graph is wrapped around the x-axis. It looks something like this. And if I see one of these problems, by the way, I'm matching your homework by my examples. If I swap those, x would be 1 minus y squared. Now, if this is too confusing for you, you could write y equal 1 minus x squared. A parabola shifted up 1 unit. And if you switch x with y, so the point 0, 1 becomes 1, 0. The point 1, 0 becomes 0, 1, and the point negative 1, 0 becomes 0, negative 1, and the graph looks something like this. So anytime you have a sideways parabola, you could switch x with y. Once you graph it, pick the main characteristic points and switch x with y. The second topic that we want to discuss would be polynomials. So those graphs will come back and forth as we move on throughout the course. There isn't a specific set where you could find this. It's just kind of like scattered all over the place. A polynomial looks like this. We look at those coefficients, they must be real, and the power on all of these variables are non-negative integers. The most important term in there is the leading term. That would be the term with the highest power. Reason for that: the end behavior of a polynomial, if n is even and the leading coefficient is positive, the end behavior will look like this. And if n is negative, it would look like this. Versus, if this power, this highest power is odd, the graph would look like this. And if a sub n is negative, well, it will switch. Anytime I think of an even, I always think of x squared. Of course, we're not getting this part, we're getting only this part. And if I see y equal x cubed, that's what a cube would look like. So as you notice, it does match the up and down, and those do match both up or down depending whether the leading coefficient is positive or negative. So again, in this section they really don't go that heavy, but again these graphs do come up as we move on. If I want to sketch a graph of this polynomial, well, if I multiply just the first terms, because I need to know what the leading term is, that's x cubed. So I know the graph behaves like this. The tough part is factoring, but in this case they give you this in factor form. The reason for that, you want to figure out where does the graph cross the x-axis. Well, that's at 0, at 1, and at negative 2. So the fact that I know this, now I know that the graph, not that sharp though, the graph looks something like this. Now you look at the powers on these variables. Since they all 1, that means around the zeros, it's going to look like y equal x, and y equal x is a straight line. So something like this. A graph must cross its intercepts. And there's a rough sketch. Now if I look at the second graph, okay, here we go. The second graph, well, this behaves if I multiply those out. X squared times x is x cubed times x, that's x to the fourth. So I know the end behavior look like this because the power is even and the leading coefficient is positive. The zeros are 0 again, 1, and negative 2. So if I can make this properly, I know that the left endpoint and the right endpoint. Now, left to right, this 0 comes from that. It has a power of 1, so you cross like a straight line. Again, whether it's positive y equal x or negative x, you can't tell. You look at this and you notice at 0, 0 comes from multiplicity of 2. Since that's a power of 2, you want to make that look like a parabola. The only way that would look like a parabola at that 0, so just around it, if it looks like this. And a graph must cross through its intercept, so it's going to come back and pass that 0 and keep on going. Now, without end behavior, there's no way of sketching these graphs. It's very hard to predict. If I look at the third graph, say, well, right, this graph looks like y equals x times x squared is x cubed, that's x to the fourth as well. So this graph looks like this at the far left and right. The zeros are a 0 right there, this is 0 at 1, and these are like the x-intercepts. Now, if I look left to right, that has, left to right, I'm sorry. Left to right, the leftmost 0 is, I messed up on the previous one, didn't I? I said this was the negative, actually it was negative 2 right there, that was my mistake. This was right there, it has a multiplicity 1. But here, this happened to have a multiplicity 1, that's why the graph didn't really switch around. Here, left to right, so left 0 comes from x plus 2. It has a multiplicity 1, so something like this. At 0, I notice there's multiplicity 1. At 1, x equal 1, I notice the multiplicity is 2. To make this look like a parabola, well, you must go up, again, just around that 0. A parabola looks like this, or like, there's no way of telling whether it's this or that. That's why you start with the end behavior and you proceed. If I look at this problem, well, this behaves like x to the fourth as well. Kind of getting old, right? A 0 right there. This is 0 at 1, and this is 0 at negative 2. Now, this looks something like that. Left to right. So this comes down and touches. I notice the multiplicity is 2, so this has to go back up. When I get to this point, I notice the multiplicity on that is a 1. Well, 1, it should look like a straight line around that. And when I get to x equal 1, it has a multiplicity 1. Again, that should look like a straight line, at least around that 0. If I look at the fourth graph, this behaves like x cubed times x is x to the fourth times x, that's x to the fifth. So it's going to point in opposite directions. If I was to ask what's the x-intercept, well, 0, 1, and negative 2. Again, I picked them that way. I notice the multiplicity on that is a 1. So when this comes up, you should make it a smooth curve, of course. So I know it's going to point downwards. As it comes up, it's going to cross and look like a straight line there. And it's going to hit this point. Now, at 0, I notice that's a cubic. A cubic looks like this, or like this. So I need to make that look like a cubic. To do that, That's how a cubic would look like. And it's going to go back up and hit that point. And I notice at 1, the multiplicity is 1, which means like a straight line, and there it is. So, the cubic you must show around that 0. And if I look at this graph, this behaves like x squared times x cubed is x to the 5th, times x is x to the 6th. So endpoint behavior, 0 at 0, this is 0 at 1, and this is 0, oops, oh boy, this is 0 at 1, and this is 0 at 1. So left to right, this comes down, and I noticed at this point, that's coming out of this, oops, man, out of this, that has a power of 1. It must pass through its intercepts. So when you get to this intercept, you notice the 0 is squared. You must make that look like a parabola, and now it looks like a parabola. Now I do look ahead and I notice that this has a cubic, so I need something like this, and connect it with a smooth curve, and there it is. The last type of problems that we look at are rational functions. And rational functions have really 4 main characteristics. The vertical asymptote, in this case, where does the denominator equal 0? That's actually, let's shrink that, 1, 2. So that's a line that you get very close to never reach. You have a horizontal asymptote, y equals 0, and the graph crosses. If you replace x by 0, you notice you get a 1. And there are no x-intercepts because the top can never equal 0. So here, well, a graph starts next to an asymptote and ends next to an asymptote. So this piece, I need to pick a point to the left of x equal -2, say -3. I just want to know if the y is positive, the graph looks like this. If the y is negative, the graph looks like this. And I know that because the graph starts next to an asymptote and ends next to an asymptote. So if I pick -3, the top is +2, that's always positive. Denominator, -3 plus 2 is negative. Positive divided by a negative is a negative, so the graph is below. And here I am aware of how that graph looks like. The reason I know it's like this, well, it must cross through its intercepts. It doesn't make sense for you to run from the bottom, cross that red line, and hit that point. So x-intercepts and y-intercepts help you a lot in sketching these graphs. Here I notice I have a vertical asymptote, x equal -2. Since the degree at the top is less than the bottom, I have a horizontal asymptote, y equals 0. And if I let x equal 0, I will get 2/4, which is 1/2. Let's say right there. Well, the right half, I already know how that looks. The left half, if I pick a point, let's say -3, the top is +2. The denominator, since it's a square, it's always positive. So the graph looks like this. Again, my option was one of those two, but since I got it to be positive, it has to be up there. And if I look at the third graph, I have vertical asymptotes. What's the domain? X cannot equal 1 or -1. So x equal 1 is not allowed, and x equal -1 is not allowed. Since the degree of the bottom is greater than the top, y equals 0 is an asymptote as well. Now, if I put x equals 0, so horizontal asymptote, y equals 0. Y-intercept, replace x by 0. If I put 0 in there, I'll get 0. And x-intercept, the top equals 0 when the bottom equals 0. So the graph passes through this point. I pick a point to the left of -1, say -3. The top is negative. -3 squared is 9, -1 is positive. Negative over a positive is a negative. That means the graph is below the x-axis. Now here I have either this option or this option. I'll pick a point between 0 and negative 1. Let's say negative 1/2. Negative 1/2 is negative. Negative 1/2 is 1/4. Minus 1 is negative. Negative divided by a negative is a positive. So it has to be that top portion. The right side either looks like this or like this. I pick a point between 0 and 1. Let's say 1/2. The top 1/2 is positive. 1/4 minus 1 is negative. Positive over a negative is a negative. And it can be both because all of these are functions. And either the last piece looks like this or like this. I pick a point to the right of 1, say 2. The top is positive. And 4 minus 1 is positive. Since positive over positive is a positive, the graph looks like that. Now, here I have vertical asymptotes x equal 2 and negative 1. So if I run this, negative 1 I can't have, and 2 I can cross. Horizontal asymptote, since the degree of the top and the bottom match, the top is dominated by x squared, the bottom is dominated by x squared. That makes this 1. Y-intercept, replace x by 0, you get a 0 because that's a 0. And x-intercept, if you set the top equals 0, that's at 0, and at negative 2. So this graph has a horizontal asymptote of y equal 1. The graph passes through the origin, and negative 1, negative 2, 0. So I have two options. The graph could start here or here, but it must pass through that intercept. So it doesn't make sense to be at the top and cross the asymptote. Instead, it's going to be in the bottom, cross that asymptote, and terminate next to the asymptote. This piece, again, I have two options. Either I come from next to the asymptote. If I run from the top, I'm going to cross that asymptote. We don't do that. Now, this graph either continues up or comes down. Again, since I'm going to have to cross that asymptote, that's not allowed. And to the right, either the graph looks like this or like this. But here, if I was to be on the bottom, I would need an x-intercept. I didn't get an x-intercept there. So it has to be the top portion. Anytime the horizontal asymptote is not y equals 0, it's a very quick graph. Here again, I factor. That is x plus 3 into x plus 1 over x minus 2 into x plus 2. So here we have two vertical asymptotes. First one is x equal 2 and negative 2. So 1, 2 can't have, negative 2 can't have. Degree of the top dominated by x squared. The leading is x squared. They cancel out. That's the horizontal asymptote, y equal 1. If I let x equal 0, I'll get a 3 over 4. Those are very important points. And x-intercept, a fraction equals 0 if the top equals 0. That happens at negative 1, negative 3. So negative 1 and negative 1, negative 2, negative 3. So the piece to the left, I know how that looks because it has to pass through that intercept. It doesn't make sense to start on top of the asymptote. The point on the bottom runs up, goes through that intercept. Now you have two options. Either you come down or go back up. But you notice there are no x-intercepts there, so there's no way you could cross the x-axis without an intercept. This is the one exception that you cross the asymptote. That happens every now and then. Horizontal, never vertical. The piece to the right, either it's going to be one of those or one of those. Since I didn't get an x-intercept there, again, that can. And this is pretty much what this section is all about. That's a quick review of 3 types of graphs. We're going to review some more graphs, but a lot more in detail. This is like a quick refresher.